Hey everyone, and welcome back to the channel. Today, we're diving into one of the most exciting developments in robotics this year. Google DeepMind just released Gemini Robotics, and this is a game changer. We're talking about AI that doesn't just understand the physical world, it can now actually control robots to do incredibly dexterous tasks. From folding origami to packing lunchboxes, this model does things that seemed impossible just months ago. Stick around as we break down how they pulled this off, what makes it different from previous approaches, and what this means for robots in your home. Let's start with the basics. Gemini Robotics is built on top of Gemini 2.0, which is Google's most advanced multimodal AI model. Now, you might be wondering, why start with a large language model to control robots? The answer is clever. Models like Gemini already understand the world incredibly well from training on massive amounts of internet data. They can recognize objects, understand spatial relationships, interpret language instructions, and reason about complex scenarios. The challenge was connecting that understanding to physical actions. The team approached this problem by asking a fundamental question. What would it take to transform a state-of-the-art digital AI model into an embodied agent that can manipulate the real world? Their thesis was elegant. They believe that if you combine the advanced multimodal understanding of models like Gemini with robot-specific training, you can create agents that understand and interact with the physical world in genuinely general ways. Before they even tackled robot control, the team realized they needed to solve embodied reasoning first. Think of embodied reasoning as the ability to understand the physical world from images and spatial information. They introduced Gemini Robotics which stands for embodied reasoning. This version of Gemini has been trained to excel at tasks like 3D object detection, predicting where to grasp objects, understanding depth, and reasoning about multi-view scenes. To measure progress, they created a new benchmark called ERQA, which stands for Embodied Reasoning Question Answering. This benchmark contains 400 multiple-choice questions, asking the model to reason about trajectories, spatial relationships, object affordances, and physics. Tests included questions like, which colored trajectory should a zipper follow to zip up a suitcase, or how to arrange objects based on their spatial relationships. Gemini Robotics achieved state-of-the-art performance on this benchmark, significantly outperforming other models, including GPT and Claude. This showed that they had successfully enhanced Gemini's ability to understand the physical world. Now, here's where it gets really interesting. Once they had embodied reasoning working, they created Gemini Robotics, which is their full vision language action model, or VLA. A VLA is fundamentally different from just a vision language model because it outputs robot actions directly. The architecture has two key components, a cloud-based backbone that does the heavy reasoning, and a local action decoder that runs on the robot itself. This split is intentional because inference on large models can be slow, but robots need to react quickly to their environment. They solve the latency problem elegantly. The cloud backbone processes images and instructions, generating action predictions in under 160 milliseconds. Meanwhile, the local decoder on the robot predicts actions for the next couple of seconds in advance, maintaining a 50 Hz control frequency. This means the robot can react smoothly even with cloud communication delays. It's like the robot is anticipating what needs to happen next rather than waiting for every command. The training data is crucial. They collected thousands of hours of real-world robot demonstrations on Aloha 2 robots using teleoperation over 12 months. This isn't simulated data. These are real videos of skilled teleoperators solving thousands of different tasks. They combined this robot data with general multimodal data, including text, images, code, and videos. This combination teaches the model both task-specific robotic skills and general world knowledge. What's remarkable is that out of the box, without any task-specific training, Gemini Robotics can solve a wide variety of manipulation tasks. They tested it on 20 diverse tasks ranging from simple pick-and-place to complex deformable object manipulation. The model succeeded on half the tasks with over 80% success rates. Crucially, it outperformed specialized baselines on tasks involving deformable objects, like wrapping wires around headphones or folding cloth, which are notoriously difficult. The model also understands language instructions incredibly well. It can follow precise commands like place the blue clip to the right of the yellow sticky notes. It generalizes across visual variations, handling new backgrounds, different lighting conditions, and distractor objects. It works with unseen objects and can even understand instructions in multiple languages and with typos. This level of generalization is rare in robotics. They developed a comprehensive benchmark to measure 3 types of generalization. Visual generalization tests if the model is invariant to changes that shouldn't affect the task, like background color or lighting. Instruction generalization checks if the model understands paraphrasing and different ways of expressing the same task. Action generalization tests if the model can adapt learned movements to new object instances or different starting positions. Gemini Robotics consistently outperformed baselines across all 3 dimensions. But the really impressive part is what happens with specialization. The generalist model is already strong, but when you fine-tune it on specific tasks with high-quality demonstrations, it becomes extraordinary. They showed Gemini Robotics learning to fold an origami fox, which requires 4 precise folds with increasing paper layers. One small error makes the task unrecoverable, yet the model achieves a 100% success rate over 20 real-world trials. Other long-horizon dexterous tasks include packing a lunchbox, which involves inserting bread into a narrow slit of a plastic bag, zipping it, transferring items into containers with lids that need sealing, and finally zipping the main lunch bag closed. Playing a card game with the robot, reading text on cards, and playing the correct cards, these tasks take over 2 minutes to complete and require precise bimanual coordination. The key insight they discovered is that diversity matters enormously. When they trained a Gemini Robotics specialist from scratch on just the specialization data, it failed completely. But when they started from the generalist checkpoint, trained on diverse data, and fine-tuned it, the model achieved 79% average success rate on these tasks. This shows that the general world knowledge learned from diverse data is critical for solving specialized dexterous tasks. Another powerful capability is few-shot learning. Instead of generating code like the zero-shot approach, Gemini Robotics can learn from in-context demonstrations. You show the model a few examples of a task being performed, and it learns to generalize to new instances. With just 100 demonstrations, it achieved over 70% success on challenging tasks like origami folding or lunchbox packing. The model essentially learns from examples entirely within the prompt without any parameter updates. This works because the model receives observations, actions represented as robot poses, and language descriptions of what's happening. The multimodal model can ground its understanding of the task from multiple angles and apply that understanding to new scenarios. It's a form of in-context learning that rivals fine-tuning, but happens instantly. Perhaps one of the most exciting findings is the model's ability to adapt to completely new robot embodiments. Starting from the Aloha 2 train checkpoint, they fine-tuned Gemini Robotics to control a bi-arm Franker robot with parallel grippers and an Apollo humanoid robot with 5-fingered dexterous hands. The impressive part is the model transferred its robustness and generalization capabilities across embodiments. It maintains strong performance on visual generalization and action generalization tests, even after adapting to new robot form factors. This is crucial for practical deployment. Rather than training separate models for every robot, you can use one foundation model and adapt it with relatively small amounts of data. This could dramatically lower the barrier to deploying robotic systems. How does this compare to previous robotic systems? Traditional robot control relied on explicit programming and hand-designed controllers. Imitation learning learned from demonstrations, but struggled with generalization. Diffusion-based policies like diffusion policy learned smooth movements, but often needed careful tuning for new tasks. Early VLAs like RT2 connected language models to robot control, but often required careful system design with multiple separate modules. OpenVLA was a significant step forward, demonstrating open-source VLA capabilities, but it still had limitations in dexterous manipulation and generalization. Gemini Robotics represents a shift towards more unified models, where understanding and action are deeply integrated within one powerful architecture. The key difference is the foundation. By starting with Gemini 2.0, the team inherited a model that already excels at visual understanding, spatial reasoning, and language comprehension. This gave them a massive head start compared to training VLAs from scratch. They didn't need to compose multiple expert models. Everything works within one coherent system. What does this mean practically? Well, first, in manufacturing, robots could understand complex assembly instructions and adapt to variations in parts without extensive reprogramming. In warehouses, robots could sort diverse items, handle exceptions, and adapt to new inventory. In healthcare, robots could assist with patient care, understanding verbal instructions and responding appropriately. The home is another frontier. Imagine a robot that understands your voice instructions, visualizes what needs to be done, and adapts to your specific kitchen layout or object preferences. You tell it to prepare ingredients for lunch, and it figures out the sequencing and handles unexpected situations. There are also research applications. The embodied reasoning capabilities could be used for better robot simulation, for planning complex multi-step tasks, or for robots that learn from human feedback more effectively. Now, let's talk about the elephant in the room: safety. The researchers took this seriously and developed specific frameworks to address it. They introduced ASIMOV, which stands for Assessing Safety Alignment of Embodied AI Models. This includes multimodal contexts where the model needs to identify undesirable or dangerous instructions even when described realistically. They found that with appropriate constitutional AI training, where you give the model safety principles to follow, the model can learn to reject harmful instructions. For example, when told to pour boiling liquid into a trash bin, the model correctly identified this as dangerous. When asked to balance on a chair to reach something, it suggested safer alternatives. The traditional robotic safety measures still apply too. The model's output needs to be interfaced with lower-level controllers that enforce physical constraints like obstacle avoidance and force limits. You can't just send raw actions to a robot. You need safety-aware motion planning in the loop. The researchers were honest about limitations. For very fine-grained manipulation, where centimeter-level precision is needed repeatedly, the model's accuracy might not be sufficient. The model still struggles with extended reasoning over long video sequences. Numerical predictions for specific coordinates can sometimes be imprecise. Future work will focus on enhancing the ability to handle complex scenarios requiring both multi-step reasoning and precise execution. They want to use more simulation data to increase data diversity and quality. They're working on zero-shot cross-embodiment transfer, so a model trained on one robot could immediately work on a completely different robot without fine-tuning. What we're seeing is a fundamental shift. For decades, robots were trapped in a paradigm where every new task meant extensive engineering and programming. Now, with Gemini Robotics, we have a model that understands the world like humans do and can translate that understanding into physical action. It's not perfect, but it's a step change in capability. The model can understand open vocabulary instructions, meaning it's not limited to predefined task vocabularies. It understands spatial relationships and physics in ways that previous models simply didn't. It learns from demonstrations in ways that feel intuitive. These aren't just incremental improvements. They represent a different way of thinking about robot control. We're moving toward a future where robots aren't specialists trained for specific tasks. They're generalists with broad understanding and the flexibility to adapt. That's powerful because the real world is diverse, variable, and unpredictable. General-purpose AI combined with embodied interaction might finally crack the problem of robots that can help with the messy complexity of real-world tasks. Gemini Robotics represents a substantial step toward general-purpose robots. By combining the embodied reasoning of enhanced vision language models with robot-specific training and clever architecture choices, Google DeepMind has created a system that can handle a remarkable diversity of manipulation tasks, generalize across visual and instruction variations, learn new tasks quickly, and even adapt to new robot forms. Whether this is the approach that ultimately dominates remains to be seen, but the results are genuinely impressive and point toward a future where AI truly interacts with the physical world. If you found this breakdown helpful, please hit that like button and subscribe for more deep dives into cutting-edge AI research. Thanks for watching, and I'll see you in the next one.